All right. Yeah, thanks. So I'll try not to go over so we can all get lunch. So I want to talk about fairness, which we heard a little bit about yesterday, and is certainly beyond differential privacy. And everything I'm going to talk about is joint work with my colleague Michael Kearns and our student Saeed. And I should say that I originally prepared these slides for like a 1-hour theory seminar that I gave at Columbia last week. I went and deleted a lot of the proofs, but not all of them. But I don't need to get through all the slides, so definitely feel free to ask hostile questions midway through. So to set the stage, and this is not an audience I need to set the stage for, but as we've been using machine learning in increasingly consequential domains, it's perhaps not surprising that there has been a sense of unease and concern that learning technologies, when placed in parts of decision-making pipelines where we would normally expect human decision makers to have a burden of moral obligation, that we're sort of worried that these learning algorithms are violating these social norms. In particular, in this particular case, that they might be exacerbating sort of human discrimination or perhaps adding their own. Okay, so we might be worried that these machine learning algorithms are being unfair. Oh, but as we've come to realize during this workshop, definitions are tricky. Okay, we can say, I think that something was unfair, but if we want to go in and fix that, if we want to embed a notion of fairness into code, then unavoidably we have to try to be precise about what we mean. Okay, and so I want to spend the first part of the talk just going through a little exercise where we try to think in a particular toy situation, what we might mean when we say that something's unfair. Okay, this is maybe also getting to another theme that's sort of come up in this workshop as we've talked to folks who come from different disciplinary backgrounds. The disciplinary background I come from sort of values simplified models, not because we believe that this captures the richness of the human experience, but because there's sort of value in modularity. Okay, so I'm going to think about a particular scenario in which a lot of the things that lead to unfairness in the real world, like data quality, are sort of assumed away. Okay, not because I don't think that these are important, but because I want to sort of focus in on one particular kind of cause of unfairness and think about it carefully. Okay, so let me show you a toy example. Okay, it's a toy in many respects. Obviously a toy, but it sort of illustrates one way in which unfairness can creep into a learning procedure, even when it wasn't somehow directly embedded in the data. Okay, so imagine maybe a scenario in which we're doing college admissions. Okay, we've got a bunch of students, and there's only two things in this toy scenario we can observe about a student. Maybe their SAT score and their GPA. And there's something that we're trying to predict, some well-defined thing we're trying to predict. Doesn't matter for the purposes of the toy example exactly what it is, but you could imagine, for example, I'm trying to predict whether they will, if admitted, to graduate within 5 years with at least a 3.5 GPA. And suppose I've got some historical data to this effect. So the positive examples are students who did do that. The negative examples are ones that didn't. There are, of course, all sorts of complications about how I might have collected data like this and whether I collected it from the right population, whether there was sample bias. But again, I want to assume all of that away for now. So I've got the data. This is the data. And there's two populations. There's a green population and there's an orange population. Right now I'm just showing you the green population. Okay, so I want you to observe a couple of things. First, slightly less than half of the green population is qualified, in the sense that slightly fewer than half of the examples are pluses rather than minuses. Okay. And second, there's a pretty good but imperfect linear decision rule which separates these two populations. So I can draw a line through space, and by and large, the examples above the line are positive, the examples below the line are negative, but not exclusively. Okay, this is the green population. Now, I told you there are two populations, so let me show you the other one, the orange population. Okay, and there's a couple of things you might notice right away. The first, maybe, is that there are just fewer orange points than there are green points. The orange population is a minority, and by that I don't mean anything except that literally there are fewer of them. Okay. The next thing you might notice is that these points, these orange points on this axis, they're sort of uniformly shifted down, in that they sort of seem to systematically have lower SAT scores compared to the green population. Okay. Toy example, but again, you could imagine that this is for any number of reasons. Maybe the green population takes SAT tutoring classes, they take the exam 3 times, they report only the highest score. The orange population doesn't. They take it once cold and report that score. That would tend to systematically lower their SAT scores. But the aim of the college, the aim of this classification process is not to admit people with high SAT scores. It is to admit people who have a positive label. And from that perspective, the orange population is actually better than the green population. A larger fraction of them are qualified. There's exactly half positive examples instead of fewer than half in the green population. And it's even easier to distinguish the positive examples in the orange population. There's now a linear decision rule that makes this distinction perfectly. Okay. So the orange population, from the point of view of this decision-making task, would seem to be the better population. They're more qualified on average, and it's easier to tell apart the qualified members from the unqualified members. Now here's the two populations together. And suppose I do the seemingly reasonable thing. I say I would like to learn the linear decision rule which minimizes classification error. I'm not going to use race as a feature because I don't want to inject racial bias. Okay. When I do that and I feed it into my optimization algorithm, what will come out is this decision rule, just the one that best fit the green population. It will have the property that every member of the orange population is rejected. Okay, it's sort of easy to see why this is the case. By the way, what could I do? I could shift down this decision rule and to better classify the members of the orange population. That would have the effect of having worse classification error on the green population. And if I'm minimizing my average error, then it's not worth it, because there's more green people and they therefore contribute more to average error. Okay. So somehow the data was, there was not bias embedded in the data. I did the seemingly reasonable thing of learning the linear decision rule to minimize classification error, and yet despite the fact that the orange population was better qualified for the task at hand, they were uniformly rejected. Seems unfair, whatever that means. Okay.
Can I just, for clarification, so the algorithm that produces your classifier here, in this process you assume that no information about the color is positive.
That's right. A useful observation, one not directly related to my talk, but a point I often make when I show this slide, is that you could do better, obviously, if you allowed me to train a different classifier for the orange population and the green population. It's a sort of a gut reaction, if I want fairness in machine learning, is that I should not allow the classifier to make use of race. This is an example where it's exactly reversed. You could only be fair, maybe, we haven't said what that means, by allowing the classifier to use race. But that's a good thing to keep in mind. Okay, a lesson from a toy example. Okay, so let's think about it. So I think hopefully, I've convinced you that something about this is unfair, whatever unfair means. In this particular example, not trying to extrapolate beyond this example, let's think about why we felt this classifier was unfair. And maybe a way to begin asking that question is to ask the question, who was harmed? Who was harmed by the mistakes made by my classifier? And one reasonable answer is that the people who were harmed were the qualified applicants who my classifier mistakenly rejected. Maybe if I somehow admitted exactly the people who were qualified, that would seem okay. Right? Someone sort of, the people who were rejected, maybe Gal called those bummers. It's like a bummer, but it was the correct decision. But somehow maybe the people that it's these orange positive examples that we might view as the people who were harmed. They should have been admitted, and yet we didn't. Okay. And so this is one of the things that might lead you to start thinking about the false negative rate. Right? If the people who are harmed are the false negatives, the people who were mistakenly labeled as negatives, who should have been labeled as positives, then perhaps the false negative rate is somehow getting at the rate at which harm is being done. Okay, I'm going to keep clicking. But
question is,
yeah.
Can I say there's some sense in which, if orangeness is a sort of identity for this group, then the orange group as a whole is being harmed by, all of us orange people are being harmed because we're not represented.
Sure. Yeah, I'm gonna talk about like groups and individuals in just a moment. So this might be a way that you would motivate what has become a very popular definition of fairness, which is that perhaps, like what I might mean by fairness, that the thing that I might object to in this picture is that the rate, the false negative rate on the green population is very different than the false negative rate on the orange population. The false negative rate on the orange population is 100%. All qualified applicants are rejected. It's much lower on the green population. This was, for example, in the sort of very well-publicized ProPublica article about the Compass recidivism prediction, the metric that was used to flag unfairness. The false positive rate and false negative rate in this example of recidivism prediction was very different between racial groups. Okay. Many other people have proposed this as a definition of fairness. And more generally, this is an example of a general family of statistical definitions of fairness, which you can generally, manufacture with the following procedure. You partition the world into groups, okay, generally according to some protected attribute, like race or gender. Then you pick your favorite statistic of a classifier, false positive rate, false negative rate, positive predictive value. There's dozens of these. And then you say that the statistic should be approximately equalized across groups. There's a lot of definitions of this sort. And if you think about it, these statistical definitions of fairness, although they have some very nice things in that they're extremely easy to check and they're actionable, they're just constraints on statistical properties, are maybe not quite what we wanted. And let me, again, try to convince you of this with a toy example, obviously a cartoon, but something that does manifest itself in real data when you train classifiers with these constraints. Okay, so imagine we've got a, hypothetical world in which we've got gender, male and female, and race, blue and green, and I decide I want to protect both, so I would like to equalize false negative rates across blue people and green people and men and women. And suppose the thing I'm trying to predict, like whether you're qualified for college, uncorrelated with all of these things. It's just a flip of a coin. One classifier which satisfies these constraints is I will admit everyone to college if they happen to be a blue man or a green woman, but if you happen to be a green man or a blue woman, I will admit you with probability 0. Okay, this does equalize false negative rates across rows and columns, okay, but it's cold comfort if you happen to be a blue woman. Okay, so this is a cartoon. Similar things happen on data when you try to apply these sort of algorithms from the fair machine learning literature. And maybe it's like pointing at perhaps that these statistical fairness definitions weren't getting at exactly what we meant, even though maybe we were concerned about false negatives. Okay, the problem is, like, when maybe like the problem with equalizing the false negative rates is not with the word false negative. Okay, we might feel in certain situations that it's the false negatives who are harmed. The problem is with the word rate. Okay? So when we've been saying false negative rate, the word rate has really meant an average over a population. Okay, and so the promise, if I say that my classifier is equalizing false negative rates, what it promises you is nothing unless you go through the unless you imagine yourself to be a uniformly random member of your population. Okay? If you happen to know something else about yourself, like you know both your race and your gender, what the cartoon showed us is that it might really promise you nothing. So, okay, so I want to go through the thought exercise of maybe we'll stick with the definition. I want to equalize false negative rates. I like the word false negative, and I want to rethink what the word rate should mean. Okay, there's a couple of things you might imagine the word rate should mean. Okay. One from sort of, we thought about a little while ago is like maybe what false negative rate should mean. What rate should mean is not an average over the population, because that's not a promise to you. Maybe what false negative rate should mean is purely over the randomness of the classifier. This would be a definition more in the spirit of differential privacy. So maybe something that said, look, the false negative rate on me should be equal to the false negative rate on Stephen. Okay? Which would mean, since the only people who can be false negatives are the people who truly have label positive, that for any two individuals, we no longer have to specify groups. For any two individuals who are both positive, who are both qualified for college in our example, the chance over the randomness of the decision-making procedure that they're rejected from college should be the same. Okay, the false negative rates are going to be the same on me and Stephen. This is what I would call a kind of individual fairness. It's not the metric fairness we've heard a lot about, but it's a different kind of individual fairness in that the constraint is enunciated on pairs of individuals. It's a promise made to individuals. Okay. And it's something we studied in a paper back in 2016, but this is somehow too much to ask for. Like, we were able to, under sort of strong assumptions about what the data distribution looked like, in stylized settings, do something non-trivial under this definition. But, if you're not willing to make those assumptions, then it's not too hard to see that, there's nothing non-trivial you can do while satisfying a definition like this. Essentially because if I have substantial uncertainty about what an individual's label might be, as I will inevitably in a real situation, this is going to tie my hands too much. So I want to think about a different thing that rate might mean. And I want to hypothesize that certainly in not all situations, but in some situations, individuals might be subject to more than one classification task. So for example, if you're applying to college, it might be that you apply not just to one college, but you apply to many colleges, each of which use a different admissions rule. It might be that in an online advertising setting, over the course of a month, say, you are shown not just one targeted ad, but thousands of targeted ads. Okay? And so I want to take advantage of that. And so here's the idea. Okay? I want to explicitly postulate not just a distribution over individuals, as is standard in the machine learning literature, but explicitly a distribution over problems as well. Every individual will be subject to a number of classification tasks. Those tasks are themselves drawn from a distribution. And what I'd like to do now is find not just a single classifier, not just a solution to a single classification task, but a mapping from problems to classifiers, a way in which, given a new task, I can come up with a new classifier so that I can promise, for example, that the false negative rate is equalized across people. So again, I don't want to define groups anymore. I want to say the false negative rate for me is the same as the false negative rate for Katrina. And I have to redefine rate. Rate no longer means an average over people. That wouldn't make sense if I'm promising this to individuals. Rate no longer means only over the randomness of the classifier, although I will allow the randomness of the classifier to be, to contribute to the computation of the rate. What I mean now primarily is over the randomness of the problem, sampled from the distribution. Okay? So if you are subject to many classification tasks, this would mean, for example, the fraction of the time that I am harmed by the classifier in the sense of being a false negative is not substantially larger for me than it is for anyone else. Okay. And this is, again, an individual definition of fairness in the sense that it is a constraint binding on individuals.
Well, you asked for hostile questions. So,
yeah, perfect. Yeah, you're perfect.
I mean, no offense.
I would expect nothing less.
I mean, you wanted the average rate for you and Katrina be the same, but what can I do? Katrina is far more talented than you.
That's reflected in the label. So again, I'm not asking that I'm accepted to the same number of universities as Katrina. I'm asking that when I'm qualified, right, the probability that I am qualified but rejected should be the same for both of us. So the fact that Katrina is far more talented than me is something that is allowed, like that is a good justification for having more success, that's captured in the definition I'm proposing.
But so the label now is this multi-label across the k-tasks?
So I haven't told you what the model is. If you can save your hostile question until I've shown you the model, that would be.
But we know it's wrong.
Yeah.
It seems to collapse down, to suffer from the fact that when we try to label people in a binary fashion, we're losing a lot of information. In particular, maybe it's fine that somebody who is extraordinarily well qualified always gets accepted, whereas somebody who's qualified but not nearly as much so never gets accepted.
So you're just objecting to like the setting in which there are binary labels.
Yeah.
You
So
could-
Are you gonna?
In which the
Or
underlying.
similarity.
Where you can
Or similarity on the basis of
Just the
that binary.
positive.
Yeah.
Right,
So you could certainly imagine talking about this in a setting with more complicated labels. That's not, binary labels are not fundamental to this construction, but it is the case that in this talk I'm going to talk about binary labels.
Yeah, somehow it's not just that, it's that we're using the same labels to talk about fairness as we're using to talk about the types of the people. And you
So
might separate this a little bit.
So it's certainly the case that you have situations in which you do not want the fairness metric to be aligned with the labels. I think sometimes they are. Okay. So,
Just one more clarifying question.
good. Yeah, save you from the next slide.
I was anticipating that. So you're also assuming that across the different classification models, there's sort of no priors on which labels should be treated in which way, right? I mean, it's all basically discovery of the data. You're not imposing any restrictions on this category always needs to be. I mean, there's no deterministic element in it, I guess.
All I'm asking for, and is that false negative rate should be equalized. This is sounds, when I say it, sounds very similar to what many people ask for when they say fairness, including like Julia England in the sort of ProPublica article. But I'm doing so with a different thing that I'm averaging over, which allows me to talk about individuals rather than groups. But that's it.
Okay.
Okay. So I'm not going to have time to get through most of it, but let me just for those those who like reading math, tell you what the model is, and then I'll skip ahead and tell you what the theorems are. Okay. So we postulate, as usual in machine learning, an unknown distribution over individuals, distribution over features, and now also an unknown distribution over problems. What is a problem? It's just some function mapping features of individuals to labels. Okay. And we're going to learn over some hypothesis class, which is also a function mapping individuals to labels. And I'm not assuming that the true labels have any nice structure. This is what would be called agnostic learning if you're a theoretical computer scientist, or just machine learning if you weren't. Which just means that there's no assumption that the functions that are these sort of unknown functions which define the ground truth are in the class that I'm learning over. And our task is to find somehow a mapping from problems to hypotheses. So given a new problem, I need to figure out what my hypothesis will be for classifying under that problem. And what does it mean to see a new problem? Well, obviously I can't tell you this function f. That would be, what would that be modeling? Instead, when you see a new problem, the way I imagine that being represented to you is that on your training data of individuals, you see a new vector of labels. You see how the individuals in your training set are labeled under the new problem. Okay. Okay. So, since false positive rates and false negative rates are complicated, let's just think about error rates, but you could do all of this with false negative rates. We can define the error rate on an individual. Okay? This is just the probability that they are misclassified in expectation over a draw of a new problem from the problem distribution. Okay? The overall misclassification rate is just the expectation of the individual misclassification rate over a draw from a person. And with that notation in mind, we can define our benchmark, the thing we'd like to achieve. We would like to find a mapping from problems to classifiers that minimizes our average error subject to the constraint that, for example, for every individual, the error of that individual is the same, or almost the same. Okay. A data set will have, the thing we'll have to work with is a data set, which is just a set of n individuals sampled from the individual distribution, and a set of m problems sampled from the problem distribution. So it's just represented as a table with n people and feature vectors, and for each of them we have m labels corresponding to each of the m problems. Okay. So blah blah blah, blah blah blah, blah blah blah. Blah 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 blah. Okay, so so there's an optimization. There are two problems we need to think about. There's an optimization problem, like how do I actually computationally find a solution of this sort, and there's a generalization problem. If I find a solution that has the properties I want in sample, how do we do it out of sample? First theorem is that the optimization problem is solvable if you can solve learning problems absent this fairness constraint. So if you believe that you can learn linear separators, you can also learn linear separators subject to these individual fairness constraints. Okay. Then there's the question of generalization, which is, in order to even think about generalization, we have to describe what this object is that maps new problems to hypotheses. But that comes out of the algorithm, which I didn't have time to show you, so, forget that. What I want to mention is that the generalization question is a little more nuanced than we normally think, because we now need to generalize in two directions. Right? Our data set consists of n individuals and m problems. And what we guarantee in sample is that we've found the classifier that minimizes our error in sample, such that for these particular n people, their error, the error rate for those people is approximately equal for these particular m problems. But we want to be able to offer a promise to new people we haven't seen before, and we want that promise to refer to new problems we haven't seen before. And so ultimately we want to promise that if we were to go in both of these directions simultaneously, sample an entirely new data set and an entirely new set of problems, that if we applied the rule we learned mapping problems to solutions, that we would satisfy our fairness constraints here as well and be approximately optimal there as well. Well, you can do that. Assuming that the number of problems you sample is sufficiently large, not that large, polynomial, and all of the things you care about, and the number of people you sample is sufficiently large, then if you solve this in-sample problem, you've also solved the out-of-sample problem.
I'm sorry, so the output of your algorithm is an algorithm that will learn on a new problem?
Yeah, if I didn't get a chance to tell you the form of this function phi, which is sort of important to understanding this, and we can talk about it later. But yes, the object output by the algorithm is a little bit non-obvious.
Right.
It's represented by the dual variables for the RM problem. But yes.
Do you assume that the different problems have the same weight?
You don't have to. You don't have to define the average error rate or average false positive rate in an unweighted fashion.
But that would also
But you do
mean
have
that
to
you're more
define it.
likely to see.
You would have to commit to some definition, yes, and you.
And this is not a mathematical decision, of course, which
That's
problem.
right. Okay, we all like pudding, but let me just end up here. The paper should be online soon. I hope you read it. And let me shamelessly plug a book. Michael Kearns and I have a book coming out in October. It's called The Ethical Algorithm. And it'll cover a lot of the issues that we have talked about at this workshop, privacy and fairness, and the tension between formalization and ethical norms.